Hello everyone. In the last lectures, we learned that a protoplanet with radius larger than 1000 kilometers can keep atmospheres. In this section, we will find structure of atmosphere of a protoplanet. Structure of atmospheres. We use similar equations to describe the structure of a star. The atmosphere maintains hydrostatic and thermal equilibriums. We assume that the energy is supplied by the accreting planetesimals. So first three equations, hydrostatic, radiative transfer, and the ideal gas equation is same with the equation we use to describe the structure of stars. The last equation is the energy supply. Energy is supplied by the falling planetesimals. Planetesimal is captured by a protoplanet. The gravitational potential energy of a captured planetesimal is used to heat the atmosphere of a protoplanet. So energy supply of L is given as a parameters to determine the structure of atmospheres. So we use the first three equations, hydrostatic, radiative transfer, ideal gas equation, to describe the structure of atmospheres. By combining the three equations, we'd like to find the temperature distributions. So let me write down the three equations. dP dr equal minus rho g mr over r squares. So we consider the protoplanet composed of a core and atmospheres. M sub r is a total mass inside of the radius of r. The atmosphere is a shaded regions. So we use this is the first equation. Second equation is round T round R equal minus 3 over 4AC kappa rho over T cubes L over 4 pi R squares. This is equation 2. P equal K over mu M sub H rho T. This is the equation 3. So we use these three equations. So from the equation 2, we move the T cube to the left hand side. Then it becomes round T to the fourth round R equal minus 3 over AC kappa rho L over 4 pi R squares. This is 2 primes. So if you divide the 2 prime over 1, it becomes round T to the fourth over round P equal 3 kappa L over 4 pi AC GMR. This is equation 4. So we assume the MR is very close to the mass of the cores and very close to the total mass of a protoplanet. M sub T is a constant values. Then we can easily integrate of the equation 4 equals 3 kappa L over 4 pi AC G M sub T times P. So this is the equation 4 primes. So we use a T equal P equal 0. The R is go to the infinities. By combining equation 3s and the 4 primes, you can find that rho over T cube. So you can substitute this P into this equations. Then you can find the rho over T cube equal 4 pi AC mu M sub H G M sub T over 3 kappa L K. This is equation 5. So we could find out the rho over T cubes. Then you can substitute this rho over T cube into the equation 2. Equation 5 to the equation 2. Round T round R becomes minus mu M sub H GMT over 4K over R squares. Then we can integrate over this equation. T equal mu M sub H GM total mass over 4K 1 over R. So we use the boundary conditions. T go to the 0 and the R move to the infinities. This equation number 6. So by substituting this equation 6 to the equation 5, you can find the density distribution. 16 pi AC over 3 kappa L mu m sub h g mt over 4k cube 1 over r cube. This is the density distributions. And also we find that the temperature distribution of the atmosphere of a protoplanet. Then stability of atmospheres. So we combined these two equations, ideal gas equations with the T to the fourth. You can find the relation between the pressure and densities. P cube is proportional to the rho to the fourth. So from these equations, calculate round log P log rho. Actually, this is exactly equal to these forms. Then it becomes 4 over 3. The stability condition for convection is given by this equation. So round log P, round log rho is less than the gammas. The gamma is an adiabatic index. Atmosphere of a gas giant planet composed of the molecular gas has an adiabatic index of the 7 over 5. This adiabatic index for a diatomic gas such as hydrogen molecules. 4 over 3 is less than the 7 over 5. So this means the atmospheres we study is a convectively stable because the stability condition is satisfied. We considered radiative transfer equation to obtain temperature distribution and density distribution of the atmospheres, and then we could confirm that our analysis is correct. This is the end of this session.